Well, hi, everyone. Thanks for tuning in. We're going to spend the next 20-ish minutes talking about the research opportunities here at CU in mechanical engineering, specifically around air quality. And then I'm happy to take any questions that you have too. To quickly introduce myself, my name is Kelvin Bates. I'm a new professor here. I think I can still say I'm new. It's been 1 year, so I have some time under my belt here, but it still feels pretty new in mechanical engineering in the air quality kind of niche of that. I'm also, like most of the rest of us in mechanical engineering who do air quality, I'm kind of cross-listed into the environmental engineering program. So we have a lot of overlap there. And yeah, I think you heard already kind of the details of why mechanical is a broader umbrella. It does have a more robust funding structure for PhD students. Good place to apply for that. But certainly, if you want a degree that says environmental engineering, that's an option too. We can chat about that later. Um, and yeah, I'll give you more of an introduction to myself and my research later on, but the rest of these slides go through some of the other faculty also in our department doing relevant research. So you can kind of just pick whichever sounds most interesting to you as you're trying to think of, say, faculty to reach out to or who you might want to do research with once you're here. This is our lovely view of CU Boulder from above. We are right kind of in the bottom center here at the engineering center, zooming to you right now. But I also really like this picture because it highlights, like Vera was saying, some of those other national labs that we have in town that really makes this such a great place to study air quality, among many other things. But these are some of the top research institutes, government research institutes for studying air quality, climate, and other related fields. So the NOAA facility over on the left is where I worked for a few years before coming here. They do a whole lot of monitoring of trace gases related to climate and air quality. And when I worked there, I did a whole bunch of field work, flying planes around cities in the US, looking at air quality. And I still work with them extensively. We've also got the National Center for Atmospheric Research, that's an NSF-funded center up on the hill. It's a very pretty building. And the National Institute for Standards and Technology also doing a whole lot of research, somewhat more kind of like fundamental chemistry and physics research related to climate and air quality. So that's kind of why air quality grew at CU, especially in the mechanical department, was because of this overlap with all of these research institutes nearby. You know, it's not all that common to see a big air quality cohort in a mechanical engineering department. Um, and really the reason that it's such a strong field at CU is because of this interaction with all of the local labs. And also out of that, we've grown a lot of interactions with local companies. So a number of the companies that make the kinds of instruments that get used in this research are either located right here in town or have offices right here in town. So we work pretty closely with them as well, which is a really fun ecosystem to be in. Um, it's also a good place to study air quality because sometimes the air quality is not great. That's actually pretty rare here in Boulder, but down in Denver, just down the road, is one of the EPA sites that is not in compliance with the ozone standards for the country overall. And so we have some good opportunities to work with folks down there also and look into local air quality. And in addition to those national labs in town, working extensively with us and also hiring a bunch of our students that we graduate, the statewide kind of regulatory agencies, especially the Colorado Department of Public Health and the Environment, who care a lot about this local air quality problem, end up being a place that we send a lot of students after graduating as well these days. So I'll spend the next 15 minutes just kind of walking through some of the faculty that we have in the department or kind of cross-listed into other departments that are related to air quality. But like I said, it's a pretty big cohort, especially for a mechanical engineering department. And we really study things across a really wide range of scales from the nanoscale, what exactly is happening chemically when soot particles form as they come out of a smokestack, say, or what exactly is happening as pathogens get transported through indoor air. That's Professor Nina Vance's kind of specialty, up to the much more global scale. So I'm over there on the right on the more global scale, although a bunch of us do kind of cross these boundaries, I would say. Professor Davin Henze is also over here on the right in this global scale, because we do a lot of running global models to look at the implications of emissions of pollutants on regional to global scales. So I also have some of these grayed out our professors who are not taking students either because they're now professors emeritus, or they're only kind of partly affiliated with the department because they've taken a job at one of these other research institutes in town. But they still are on people's committees and stop by. So I've included them, but really the ones in color here, the ones who may be actively taking students, who are actively participating in our department, funding allowing, I guess I'll say. So to walk through some of these somewhat more specifically, Professor Hope Michelson does a lot of work on the chemical composition and then structure of soot particles formed during both combustion and pyrolysis. Got a lot of fun instruments looking at that, mass spectrometers and X-ray and laser spectrometers as well. They do some field work on this, but a lot of lab work. And before moving here, Hope also worked at a national lab for a really long time, and so has good connections with Department of Energy national labs as well. Professor Marina Vance works especially on aerosols, small particles in the atmosphere, and these days a lot on indoor air quality. I would say Professor Vance is one of the people who really got the indoor air quality world growing and interacting with the outdoor air quality scientists really nicely, and has participated in a few of these big field campaigns where they take instruments from a whole bunch of groups, set them up in a house or just outside a house, and really extensively characterize what's going on inside in terms of indoor air quality. We actually did one of these field experiments just this last summer at Professor Vance's house. She and her family went on a road trip for a few weeks, and a bunch of the rest of us in the department brought our instruments over, set up in her garage, and measured all of the air quality that was happening inside her house, which was really fun. Great collaborative experience for all of our students. And I think it'll be some cool data for us to look at in terms of especially some of the overlap between what happens when you use cleaning products and you're cooking at the same time in a house. So Professor Vance's research is pretty hands-on. It's a lot of instruments, a lot of setting up small-scale experiments to kind of characterize what would be happening in a house, but can we bring that down to a smaller scale and look at just individual, say, cleaning products one at a time. In our big joint air quality lab facility, we actually have a little side room. It's probably 10 feet by 10 feet that we can seal off and do these kind of small experiments. Again, collaboratively, we all hook up our instruments to it at the same time. And Professor Vance leads a bunch of those. Moving right along, Professor Hannigan, who was previously our department chair and is now actually the program leader of the environmental engineering program. It's not a department here. But his work focuses especially on low-cost sensors and the deployment and development of those sensors. So trying to get them as accurate and precise as possible while still being really cheap and easily deployable, and then setting them up around places. So they recently did a deployment around Los Angeles, trying to characterize kind of the spatial variability in air quality in Los Angeles. And they also have ongoing projects setting them up around potential wildfire sites. And then when a wildfire does come through, looking at the smoke and how it travels. So these low-cost sensors are not meant to be as good as the state-of-the-art instruments necessarily, but if they're cheap enough, you could deploy a whole bunch of them potentially, and really characterize how spatially variable pollution is around, say, a city. Whereas I only have one of my instrument, I could just take it one place and say, Los Angeles is dirty today, for example. But I wouldn't have any info on how that varies block to block or east side to west side, for example. So that's a lot of Professor Hannigan's research. Professor Hannigan also helps lead a class on project-based learning in rural schools, which a lot of folks in our air quality cohort take or help out with, because it's really going around to schools in Colorado, mostly Colorado, I think, and bringing in projects that usually have to do with air quality, and setting up some of these low-cost sensors and using data from these low-cost sensors and getting this involved in both the educational sphere as well as the actual the science sphere. So people really enjoy that as part of his research here too. And he has been teaching our main air quality class in the department for a while now. So whether or not you join his group, you'll definitely interact with him when you're here. Moving further up the scale, I guess I didn't say this, but I started at the micro scale and I'm moving slowly to the macro scale. Professor Greg Rieker's group does laser spectroscopy, specifically with a dual comb laser, which I'm not going to go into the details of, but he's worked with folks right here at NIST, one of the national labs in town, to really develop this technology and turn it into something commercial in part. So he's started a very successful startup that's commercializing this instrument, but they also have been working on applying it to all sorts of different things, air quality being just one of them. But these instruments can measure methane, for example, across a really long path length. So you can set up a laser on one side of a landfill, for example, and on the other side have a sensor that sees what the laser is shooting at it, and you can calculate between there how much methane there is, for example. And they're working on applying this to also detecting particles and potentially what the aerosol composition is between there too. So it's a lot of instrument development, but these days a lot of field deployments as well. And they've had projects taking these up to Alaska to look at methane coming out of permafrost there, to the Los Angeles area, looking at methane coming out of landfills there, as well as more of the instrument development side of things in the lab. Moving up, we've got Arthur Mizzi. Arthur is a research professor here, and he works extensively with both NASA and NOAA. So it's the NOAA facility here in town. We don't have a NASA facility here in town, but a lot of us do overlap with NASA centers, either in Maryland or the Jet Propulsion Lab in Los Angeles are really the two that we work with most extensively. Professor Mizzi's work focuses a lot on improving our air quality models, especially smaller scale, kind of urban to regional air quality models, and how well we can forecast, for example, ozone pollution or particulate pollution. So it's really on the computational side of these models, less so on the chemistry per se that's in them. But how can we use mathematical methods to both improve how these models work and kind of use these models to back out where emissions must have come from. If we see something in the atmosphere, we don't necessarily know where it came from, but you can effectively run these models backwards to track out where it's most likely to have come from. And so Professor Mizzi's work is a lot of the really intense computational aspects of making that happen. Professor Davin Henze, chair of our graduate committee, is also kind of on the same side of things with the model developments, but especially using those models in concert with satellite data. So nowadays we can see a lot of air quality data. We can collect a lot of air quality data, I'll put it that way, from satellites, looking down at the Earth and seeing how light is getting either absorbed or refracted or anything like that between the Earth and the satellite. But it takes a lot of computational work to go back from that. What is that light path getting from Earth to the satellite, to what pollutants are in the air and where exactly are they located between the satellite and Earth? Are they down at ground level or are they up higher in the atmosphere? And furthermore, if we see them in that column, where did they come from originally before they blew in the winds and reacted chemically over here? And so Professor Hensey's work is a lot of combining state-of-the-art models that we have to simulate how chemicals get transported and react in the atmosphere with the satellite data that's rapidly coming online more and more. We have a pretty new satellite that started operating just over 2 years ago called Tempo that sits right over the US and stares down at us all the time, looking at air quality. So before 2 years ago, we could only ever get these satellites to pass over like once or twice per day, and they would get one screenshot per day of air quality. And now we have this one that sits up there and takes, honestly, like a screenshot every second, but like we have to average them into maybe hour-long bins. But still, that's so much more data than we've ever had before. And so figuring out what to do with all of that data and how much it can really tell us about air quality over the US is a huge task, and one that Professor Hensey's group is instrumental in, I'd say. And last but not maybe least, I am the newest after all. My group does, I would say, kind of a combination of a whole bunch of these things. We work extensively with the NOAA lab right across the street here that I worked for before I moved over here. And so with that NOAA lab, we do a lot of field observations. That's this middle paragraph here, I guess. Mostly taking instruments and putting them on airplanes and flying them around to look at air quality. So those satellites can see a whole column of air. What we want to do is fly right through it and see what is at exactly this point in the air. We actually use this a lot to validate those satellites, to figure out if those satellites are seeing things correctly or not. But we also use it to kind of help develop our instruments and help inform models. And so kind of the other half of my group right now runs atmospheric models. In fact, the same type that Professor Hensey's group runs, and compares the output of those models to our field observations to say, how well are we doing? If we aren't correctly simulating what we see, what do we need to change in order to make that happen? Frequently, it's we're not properly accounting for emissions from all sorts of weird sources, like your personal care products, shampoos and deodorants, off-gas a bunch of interesting compounds. That's the only way that they smell good. If you're smelling them, it's because something's evaporating off into the air and getting out there. And when you get enough people in one place using shampoos or deodorants or things like that, you can absolutely see that from a plane flying over the city. And we can tell that that's one of the things that models are missing these days. And so a lot of our work has gone into kind of characterizing that emission source, in addition to some of the other less well-represented ones like cooking and evaporating paints and things like that. And so we use mass spectrometers, really big and fancy mass spectrometers that cost many hundreds of thousands of dollars and can see molecules that are present at less than one molecule in a trillion in the air. Is, for example, these silicon oxide products, siloxanes, that come in your deodorant that make your deodorant the right texture, for example. But we can see them, even though they're present at really, really tiny quantities, and they help us track kind of how much emissions are we getting from these different sources. So we spend a lot of our time perfecting these instruments. And the last little bit of my research, which is actually on the top here, I probably should have put these in a different order, is taking those instruments back into the lab and running experiments on the compounds that we've seen out in the outdoor world. So when we go see these compounds from shampoos and deodorants, we have no idea how they react in the atmosphere or what they do. Are they harmful? Do they contribute to ozone or not? And so what we can do is come back into the lab and study those compounds one by one, usually by putting them into a big plastic bag and shining lights on them, which pretty well mimics what happens in the atmosphere, and then measuring them with the same instruments that we take out into the real world, and being able to kind of put together piece by piece what these things do when they're actually out in the atmosphere. So like I said, my group is still kind of getting off the ground. We don't actually have one of those instruments of our own yet, but we're probably getting it in January, and starting these experiments ourselves. But because there's so much in town for us to work with, we work with the NOAA lab, we work with the NCAR lab, and they have instruments like this, and we help them out on their experiments right now. That's most of the faculty in mechanical/environmental engineering. We do have a lot of faculty doing air quality over in chemistry, and we can work with them, but I guess not as our advisors in this specific program. But the last thing that I wanted to talk through, the last little slide here is other stuff, not just advisors and research, but other offerings that we have. So because we're a big enough air quality group here, we can offer a whole lot of different classes related to air quality. So some of our kind of staples in the department are environmental modeling, air quality measurement techniques, air pollution control engineering. That's the big one that Professor Hannigan teaches. Inverse modeling, that technique that Professors Mizzi and Henze use extensively, is also a class that Professor Henze teaches quite frequently. Aerosols and indoor air pollution right now are taught by Professor Vance. I'll probably be taking over aerosols at some point here, but right now I'm teaching a climate engineering, geoengineering class. That's pretty fun. Come sign up for it if you join us. And then, of course, because we have also the chemistry department doing a lot of air quality, the atmospheric and oceanic sciences department, the environmental engineering program, there's opportunities to take classes across campus on any kind of related fields that you might be interested in. We've got so much here in town related to air quality, and I've already talked through some of these, like the NOAA Chemical Sciences Lab and Global Systems Lab, NSF's National Center for Atmospheric Research. Those are both 1,000-person labs that are doing really cutting-edge research on air quality / climate here in town. The National Renewable Energy Lab is related in terms of its work, and it's just down the road, about 20 miles in Golden. And a lot of these labs have set up institutes, we call them, at the university, where some of their employees are actually also university employees. So the Cooperative Institute for Research in Environmental Sciences is kind of it's a program here on campus that employs NOAA employees across the street. It's a weird kind of hybrid, but what it really means is that we end up being very well integrated with these national labs here in town. And there's really no barriers or hurdles to collaborating with them and working with them. And then lastly, like I said, there's a lot of local companies that have set up, in part because this is such a hub for air quality, that we work with extensively as well. So Scientific Aviation does some of these flights that I talked about, where we put our instruments on a plane. Some of those are planes that the government owns, but some of those we can contract with a local company. For example, Tofwork is the company that makes these mass spectrometers that I talked about. So all these things are right here in town, and there's good connections with industry because of that as well. And then we have within the department a kind of monthly air quality, we call it a super group meeting, because it's kind of like our group meetings, but all of our air quality groups get together and do informal research presentations or hear from someone who's in from out of town, maybe. Last month, we used them as practice talks for a conference that a lot of folks go to, the American Association for Aerosol Research Conference. And folks just used it to practice their talks. We serve lunch. It's pretty fun. We all get to hang out. And then there's a bunch of somewhat more official kind of seminar series in town and here on campus, especially, that are related. Again, simply because there's so much air quality here and everyone wants to have their own seminar series. If you went to all of the seminars that were air quality related here, I'm pretty sure you wouldn't get any work done. So you have to be a little bit picky, but they're pretty fun. I think that's all that I wanted to go through here. And I can answer any questions you guys have related to air quality research here, the national labs or companies around town, or anything else about the program as well.